The Last Lightbender. Investigating refraction. So you really think you can trust your eyes? That what you see is what you get? Don't be too certain about it. Nature might fool you. It's quite simple. Light falls onto an object, gets reflected towards our eyes, and we see this object. Everything is nice and orderly and straightforward, because light always travels in a straight line. Or does it? Well, of course light follows straight lines. We see it every day. This is the foundation of perspective, isn't it? Straight lines are everywhere. On houses, streets, railway tracks, paintings. Just look around you, you can't miss them. Sightlines are straight, and next time you see a beautiful girl, make sure you look straight into her eyes. Whoa! But there's a problem. Sometimes our viewing line is blocked. For instance, by the curvature of Earth. And this brings us to our next question from Eric D. from T.
The Cape Lagulas Lighthouse in South Africa is 33 feet high, 238 feet above sea level, and can be seen for over 50 miles. If the world were a globe, this light would fall 1,400 feet below an observer's line of sight.
I have never been to South Africa, so let's check the facts. Eric claims the Cape Lagulas Lighthouse is 33 feet high, 238 feet above sea level, and can be seen over 50 miles. A quick search on Wikipedia says it is 89 feet high. The focal plane, where the light comes out, is 102 feet above high water, and its range, the visibility of its 7.5 million candela light, is 35 miles. Eric gives no sources for his information, whereas Wikipedia has 7 different sources. I can only guess that Eric got his facts from an 1899 book, Zetetic Cosmogony. This book claims that Earth is a flat circle, and it was written by someone who called himself Rectangle. Probably a funny guy. I thought maybe Eric's 238 feet height has to do with the elevation of the land. But a quick check on elevationmap.net shows it is only 43 feet high in this area. We come nowhere near 238 feet height, not even at low tide. Eric plainly got his facts wrong. Or did he do that on purpose? But still, we do have a visibility problem. It is not as bad as Eric thinks, 1,400 and some feet below, but the lighthouse still would be hidden by Earth's curvature. Let's quickly calculate it. There are a few online curvature calculators. The simplest ones just use the Pythagoras theorem that we all learned at school. A squared plus b squared equals c squared. If we use 2 right-angled triangles, we can put in the viewer's height, the distance, and calculate the hidden height behind the horizon. So let's do this for the Cape Lagulas Lighthouse. Let's put in a viewer's height of 15 feet. That's about the height of a person on the deck of a normal small vessel. We had a range of 35 miles and get a hidden height of 610.5 feet. So if we now subtract the 102 feet height of the lighthouse from the 610.5 feet of the calculated hidden height, we get a difference of 508.5 feet. So the lighthouse would be hidden 508.5 feet below the horizon. So how can it be seen at all? Well, we have two problems here. First, do we really have to see the lighthouse tower? Or is it sufficient to see its light in the direction of the tower? And second, all these curvature calculators use the assumption that light travels in a straight line, which it does not. I will show you why. Perhaps some of you still remember this experiment from the physics course. The teacher sent a light beam at a glass semi-cylinder and showed you how light gets bent when entering a denser medium. Later he might have shown you a double bend, which inevitably leads to the understanding of lenses. This process of bending the light at the surface of a more or less dense medium is called refraction. Refraction is stronger in denser media. What does this have to do with our lighthouse? Well, air also can have different densities. Colder air is denser than warmer air, so it has a different refraction index. Humid air is different from dry air, and often we have layers of different air density on top of each other. No way that light can go through our atmosphere in a straight line. But you don't have to take my word for it. Carl Friedrich Gauss, the famous German mathematician who carried out a geodetic survey of the Kingdom of Hanover, wrote in a letter, "On sunny days, refraction depends to a high degree on the time of the day, much more than on cloudy days. At noon and during the hours around noon, refraction is smallest. During the later afternoon hours, it regularly rises, and at sunset it certainly is not smaller but bigger than on cloudy days." So what does it mean? Carl Friedrich Gauss noticed that his measurements of heights of mountains differed from daytime to daytime, depending on the refraction index of the air. Here is a 2010 chart from Hurt et al. Showing the refraction differences in different daytimes, on sunny days and on cloudy days. As Gauss said, the differences are bigger on sunny days and in the evening hours. So if refraction can make mountains rise and fall, it can do the same to the horizon. So things that should be well hidden behind the horizon can magically appear in front of our eyes when the conditions are right. What conditions? Well, everything that makes the air denser: low temperature, high air pressure and high humidity. The effect that things get raised up due to refraction is called looming, and now we can see why it often appears above water surfaces. The temperature there is often lower, the air pressure and humidity higher. So it is no wonder that Eric D. from T has so many lighthouse examples. I won't check all his visibility claims, but it is fact that we can see much further across water surfaces. Therefore, it is not easy to prove or disprove Earth's curvature by optical alignment of objects, like in the Bedford Level experiment by Dr. Robotham in 1838. The original experiment was carried out 8 inches above the water, where refraction is strongest. We have all we need: a lower temperature, the water is colder than the air, thus cooling down the air above it, high density, air pressure is greatest near Earth's surface, and high humidity. The experiment even had to be postponed because of misty weather. Robotham himself admitted later on that his experiment did not take refraction into account. When the experiment was repeated with higher flags in less dense and cold and humid air, the curvature was seen, because the middle flag was higher than the first and the last flag in the row. And here is a little advice for everyone who does a laser experiment across a water surface. Go high up above the water to avoid problems. Some of these effects can look pretty dramatic. Have you ever seen the Flying Dutchman? Here we have a combination of refractive light bending and total reflection. And here we can see a huge ship with a flipped over reflection of it on top. The next sequence shows two things. The sun rises up from below the horizon and it does not approach us from a vantage point. And we can see a mirage as well. Do you still think light always travels in straight lines? Mirages appear when refraction is stronger than normal, on a hot day in the desert, or above hot tarmac of streets, or above cold water surfaces. It all depends on the density of the air through which the light has to travel. And the next time you see an ostrich putting his head into the sand, you might remember this video. You might say, okay, there might occur some light bending, and we sometimes may see further than Earth curvature usually allows. But can we quantify this effect? Can we calculate how far further we can see? Well, yes and no. Yes, because there's a formula that lets us calculate the refractive index of air. And no, because on long distances we have many different conditions along the path of the light that also change with time. Let me explain it to you. This is the formula I mentioned. You put in air pressure, temperature and relative humidity and get the refractive index as a result. What is the refractive index? It is the factor of how much light is slowed down by passing a medium, and it determines the angle by which the light gets bent. It can change along the path of light. In vacuum, the refractive index is 1, which means light doesn't get bent. In air, it usually is around 1.3, but there are conditions in which it can get up to 15. There are other formulae as well, where k is the coefficient of refraction. And this formula shows how the radius of the bent light beam exceeds the radius of the Earth, and thus lets you see beyond the horizon. In a way, if you think about it, long-distance visibilities even prove the curvature of Earth, because light that bends around a globe can travel further than light bending towards a flat surface. Now that we talked so much about refraction, we also should say a few words about dispersion. The refractive index of materials depends on the wavelength of the light. The blue part of the light usually gets bent stronger than the red part. This is the reason why the colors, of which white light consists, get spread out when entering a prism or a water droplet. If you look through humid air that consists of many water droplets, the colors will be spread out as well, but then they will overlay and mix again. Where they get mixed, the light becomes white again. But at the upper and lower fringes, you will see some non-mixed colors. This effect led some people to think that the International Space Station is a hologram, because in some photos of it, it has colored fringes. But you can see it is just an effect of dispersion, because on one end you have the light of short wavelengths and on the other you have the light of the longer wavelengths. In the middle the colors mix into white. My advice: take your ISS photos when the air is dry. Your night sky photos will get much better because there is less refraction.